Welcome back, everybody. In this video we're going to take a look at hydrates. So we already know what a hydrate is. We've looked at the previous videos where we looked at the format for writing a hydrate, and we've talked about empirical formulas. And so we realize that if we're working, we see here in the stem talking about using cobalt. So we realize we'll probably have an ionic compound, and remember our ionic compounds, type 1, type 2 compounds form hydrates. That's our empirical formula for those. And remember how we show the dot to show the amount of water that's bound to it. Remember, when you're looking at a formula, you're always working with moles. So eventually we have to go from mass to moles. All right. So, but we have to start with what we've got. And it looks like we don't have a lot of information here. And we don't. This problem alone, we would not have enough to work with. All it says is we have a 7-gram sample. So instead of typing out this huge amount of stuff to have to decipher, I decided what we could do was just use a picture. So I already drew this out, right? Okay. So I've drawn this out for us, and from here we can take a look and do everything we need from here. So you should recognize, right, that right there, that X represents, we don't know how many moles of water. So eventually what we're trying to figure out is solving for is our X, our multiplier, right? And so remember, that's our molar ratio, which would be how many moles of water per moles of the salt compound, the anhydrous salt compound. So the anhydrous salt compound would be the part without the water, right? The hydrate is everything. If you were to take all the water away, it would be anhydrous. It would be without water. So we can see here that it's a ratio of one of these for X number of moles of water. So that's what we need to figure out ultimately, is how many moles of water are in the compound. Okay? So here's an evaporating dish, just a quick little sketch. It doesn't have to be a huge, wonderful work of art, just something that represents it. And I recommend you do this whenever you do lab work or you're working out problems. Sketch out your thoughts. It really, really helps. So we've got cobalt chloride, and so look up the formula, and so we see cobalt. Basically, this is cobalt 2 chloride, right? Because cobalt being a transition metal, right? Cobalt 2 chloride, and some moles of water. We have a 7.5 gram sample. We know our dish is a little over 26 grams. So remember, the triangle just means, delta means heat, so heat has been added. So it looks like there was one heating, then a second heating, and then a third heating. So after the first heating, right here, after this first heating, when we let it cool down and remass it, we see that we have a mass of 31.27 grams. And then we heated it up again, we see that we have basically 30.14 grams. So it looks like it just keeps dropping and dropping and dropping. And then again we see after third heating, 30.11 grams remains. We don't know if we could have gotten more lower reading or not. Typically, though, you look for about 2 mass readings that are consecutively kind of close to each other, keeping in mind the uncertainty of the tool you're working with. And so usually, a lot of the stuff that we're using in lab, that usually will mean an uncertainty of somewhere plus or minus like 0.02 or 0.002, depending on which scales we're working with right here. So if you were to look for 2 consecutive ones in a row here, you would look for, we're going to assume 30.11 being our lowest reading, 30.13 or 30.09 would get us somewhere around what we think might be any of those would be acceptable. So we have to work with this. You should recognize that a reaction like this is it's like a decomposition reaction, right? And you learn this basic stuff in your Chem 1, right? This is a basic decomposition reaction, and we need an equation for it. So if you think about it, you've got your cobalt chloride, right? And we don't know how much water there is, so you're just writing the X. You're just writing that multiplier there. And of course, this would have to be a solid. You put it in the evaporating dish, and you heat it up. I don't care how many times you heat it up, we just need the reaction that represents this, right? When you heat it up, it will decompose into the salt product and then the water product. The two, that dot right here, this dot right here, this represents like the hydrogen bonding, the bonding that occurs between the salt and the water product, right? So if you heat it up enough, get enough energy in the molecules, you can push that water and drive that water off, and it'll evolve off as, vapor, right? So that means you could write cobalt 2 chloride, and when you're done, you would have that solid. It would probably look different. It would more than likely it would look different, right? Remember, color is a sign of chemical change. And then we would have X moles of water. Again, that's what we're trying to figure out. And since you're heating it up, we're going to show this in the gaseous phase, right? Okay. So there's our basic skeleton equation. We can't balance it because that's what we're trying to figure out is X. What we need to know is X equals what? Ultimately, that's what we have to figure out, right? Okay. So here we are. What we need to do next is just let's come up with a game plan here. So we've got 30.11 grams. That's the mass after the third heating. But if you think about it, it's the mass of the dish and whatever substance is in there, right? So right here, this represents the dish plus the anhydrous salt, right? And typically we just say, the salt. So remember, anhydrous, so A or AN in front of something means not, it negates it, so this means not hydrated. So once all the water's gone, you would call it an anhydrous salt. When the water's there, you call it a hydrate, right? So that represents that. Now, so, that's 30.11 grams. So if we were to subtract the mass of the dish, right? So, I know you can do this in your head, but let's do it. Let's go ahead and just use our calculator for everything. Minus, we got 26.1. So that would give us 4.01 grams, right? That's going to give us 4.01 grams. So if we think about it, this right here equals the mass of our salt. This is the salt product right here. Okay, that's our salt product. So we started off with 7.50 grams of our hydrate. According to this, we have 4.01 grams of this. We have calculated this out. I'll just put it in parentheses to show that this happened as the reaction. So a lot of times I'll use parentheses to separate kind of what we know versus what we're discovering. If you have some sort of organized way of doing that, I think it really helps. So now you've got 7.5 minus 4.01 gives you should see 3.49, right? So that means we've got 3.49 grams of water that evolved off of this reaction. Alright, so now we ask ourselves what we do with this. So there's our basic decomposition reaction so that we can look at what happens with our hydrate. So what do we do next? If we think about this for a second. Alright? I'm going to pause for a second. You pause this video here. Think what you believe the answer to be. And then start this video again and see if you're correct. Alright, I'm going to assume you're back and you have an answer, and I'm sure you have a correct answer. If you realize that we have to get the ratio of moles of water to moles of salt, then you are correct. If you didn't get that, let's help you understand that. So let me go ahead and move this up a little bit. We've got basically still the information that we need right here. Remember, when you look at a formula, that X represents moles of water. So right now there's 1 mole of cobalt 2 chloride, but we don't know how many moles of water. So ultimately we need to know how many moles of water for every 1 mole of cobalt 2 chloride. So right now we've got mass of water And the mass of water that we have is 3.49 grams of water. Use our molar mass. So what is that? 18.02 grams, right? 18.02 grams of water. And that will be for every 1 mole of water. All right. Remember, it's all about those units. Got to get rid of those units. Got to get rid of those units. All right, so let's do some. Let's punch it in. 3.49 divided by 18.02. Double check. We should get 0.19367. We can stop right there, right? 0.19367, and of course, that is moles of water. Okay, let's move on to the next step here. Oops, I didn't mean to keep forgetting. I'm on a Mac, and I've got all these wonderful gestures on both my trackpad here and my Wacom tablet that I'm using to write on the screen. If I'm not careful and I bump it, it does stuff. So, all right, so we've got mass of the anhydrous salt, and I know a lot of you say, do I have to write all of this stuff? If you write everything, if you stay organized, you're going to find that this stuff is really, really not as confusing as you think. All right. So the mass of the salt. So let's come up here. We had 4.01 grams. So we've got 4.01 grams, and this is our cobalt 2 chloride. All right. And so we need to figure out. All right. So we go to our cobalt, so we've got 58.93, right? So that's 58.93 plus cobalt 2 chloride, so there's 2 chlorines. Right here, chlorine 35.45, so that was plus 35.45 times 2, 129.83. Double check my math, we should get 129.83. Okay. So let's go back to our whiteboard. What did we say that was? 129. I have a bad memory. 129.83 grams of cobalt 2 chloride. And then, of course, it's per mole, right? Because it's molar mass. Get rid of that unit. It's so important. Everything is about unit. Once you understand this stuff, you'll realize that you can basically dimensional analysis your way out of almost any kind of math problem in chemistry. Just about. It's because it's all about the units. If you get the units right, you're going to get the calculation right. All right, so we've got 4.01 divided by 129.83. All right. Should get 0.3125, right? So, if you were paying attention, you noticed the Tib did what is common for a lot of people, which is I made a mistake. So I didn't even think about it. So partway, when I was doing this part right here that says 0.19 in the back of in my mind, I kept thinking, man, something about this doesn't look right. But I just rolled with it because I was like, well, I punched in the calculator. I'm pretty sure I punched the numbers in correctly. And then as soon as I divided this out right here, I got a point something, and I realized I shouldn't have point something. I should have a number point something else, right? That I can evaluate to an integer value. So I had to think about it. So yes, if you go back, you'll notice that 4.01 divided by 12.83, I forgot the value. If you look at cobalt, that's 129.83. That was just off by, a factor of about 10. And which makes sense because I had a 0 point something and then a number instead of a number point something else. I was off by a factor of 10. So with that said, I'm going to scroll down to where we have the corrected value, right? So everything is the way it's supposed to be, right? So 4.01 divided by 129.83. That 129.83, remember, that is the molar mass for the cobalt 2 chloride. So 4.01 being the mass of the salt that we have in this particular experimental data. So I forgot that 9, highly important, changed everything. But instead of completely scrapping the video and remaking it, this is a good learning moment. So this is what you do. You look at numbers and you go, man, that doesn't make sense. So instead of sitting there for a second trying to figure out what I did wrong, I just stopped that video and started fresh again. So let's jump back. Let's jump back into learning how to do this thing. So we realize that right here on the bottom we've got 0.0308886, and we can see right here that 19 divided by 3 is somewhere around 6, right? So let's see here. So we've got 0.19367 divided by 0.030886, and we get 6.27. Alright, so let's think about this for a second. We've got 6.27, and what else we got? Let's put a couple of the numbers. 0.47. And of course that is moles of water, right? Per, obviously now that we've reduced the fraction, this is 1 mole of the cobalt 2 chloride, our anhydrate, right? So how do we interpret this, right? How do we interpret this? Well, so we know X now has to basically be 6, right? So now so you see 0.27. So whenever you see something like this, there's two ways really to interpret this. So 6.27, is it closer to 7 or is it closer to 6? So obviously it's closer to 6. So we have basically a 6. We have a 6 to 1 ratio. We have a ratio of 6 moles of water to 1 mole of the salt. The second thing that should immediately you should be aware of is 0.27. You realize 0.27 of a mole seems like a lot, right? It seems like I mean, if we're not careful, if suddenly that were to double, we'd be at 6.5, and we'd have half a mole, and that's very significant. So the first thing you should look at this and go, okay, 6 is probably a good answer. The 6 to 1 ratio is probably a good answer, but there's probably error in this. And if there was less error, I would probably get a value that's closer to 6. So I would have a value that's less than 6.27. So I'll link up in this video here towards the end where we can go to another video and basically figure out how much error do we have in this, and that'll help put this in perspective. All right. But essentially what we have here is a 6 to 1 ratio. So we had cobalt 2 chloride, right? So now that we know that X equals 6, then we know that our formula is COCl2 dot, represent the bonding, 6H2O, and we would name this cobalt 2, because remember it's a transition metal, chloride, and the 6, our prefix is hexa hydrate. There's our answers. Alright, so go back, rewind that. Remember, you always want to look for the information in your reaction, get your basic decomposition reaction for your hydrate written out, and then from there we're just figuring out our X value, which is basically our multiplier, and then it's all, once you know the mass of everything, you're just basically converting mass into moles, looking at the ratio of moles of water to moles of salt, and then whatever that ratio is, you now know that that's what your that's your mass of water in your hydrate. And you just write the formula out, then you name it accordingly using your prefixes, for 1 through 10 or whatever the case may be. And there are hydrates where there's like 24 moles of water in there, and there's some crazy ones. We won't do anything like that in this class, but in research or in like an AP chem class, you could be expected to understand how to do that. But same type of math, just different numbers, more complex compounds. There's more complex metal compounds than what we're working with in class that would sort of result in those things. All right, hope this helped. Pause, rewind, do what you need to do, and good luck. And that means that we're going to wind up with something that's somewhere around 6, according to these numbers, right? So let's see what happens. Let me see, 0.19367 divided by 0.31254. All right. On to the next problem. Thanks for your patience. We'll get it right next time.